For decades, they've been this staple of science fiction, right? Walking across our movie screens, through the pages of our favorite books. But humanoid robots, they're actually starting to step out of that fantasy world and into our reality. So I thought, let's really dig in. Let's peel back the curtain and see what actually makes these things tick.
And it really all starts with this one simple question. Out of all the possible designs, all the shapes a robot could take, why do we keep coming back to the human form? What's the actual advantage of building a machine that looks, well, like us?
To get to the bottom of that, we have to look past the sci-fi stuff. This isn't about just building a cool-looking character from a movie. It's about some really specific, really smart engineering logic. Okay, so first things first, let's get on the same page. When we say humanoid robot, we're talking about a very specific blueprint, a machine built to mimic the basic human structure. We're talking a torso, a head, 2 arms, 2 legs. And this is totally deliberate for some very clever reasons. And here's the why broken down. First, by trying to build a robot that walks on 2 legs, we end up learning a ton about how we do it. It's like reverse engineering ourselves. Second, and this is a huge one, our entire world is built for us. Think about it. Stairs, doorknobs, car seats. A humanoid robot just fits right in. The world doesn't have to adapt to it. And finally, there's us. A machine with a familiar shape just feels more natural, less weird to interact with. It's designed for our social world, not just our physical one.
All right, so how do you actually build one of these things? Let's pop the hood and take a look at the core components, and we'll use the human body as our guide. It's a pretty great analogy.
So, just like us, it all starts with perception, with understanding the world around it. But instead of our 5 senses, a robot has this whole suite of electronic sensors, constantly feeding it data. And this shows you exactly how technology mimics biology. Cameras are the eyes, microphones are the ears, tactile sensors let it feel pressure, touch. But that last one, proprioception, that might be the most important one that we never think about. It's how you can close your eyes and still touch your nose. For the robot, it's like an internal GPS for its own body, telling it exactly where every single limb is at every single moment. Without that, it couldn't even stand up.
Okay, so once the robot senses the world, it has to be able to do something about it. It has to move. And where we have muscles, a robot has actuators.
Just think of actuators as the robot's entire muscle system. These are the powerful little motors that take electrical energy and turn it into pure physical motion, the oomph it needs to swing an arm, bend a knee, or grip something. Literally every single movement is powered by these guys.
And finally, something has to be in charge of all this, right? The sensing, the moving, it all needs to be coordinated. We need a brain. And for the robot, that's its control system.
This is the command center, the mission control. It's a super powerful onboard computer that is just constantly drinking from a fire hose of sensor data, making sense of it, and then firing off thousands of precise commands to all those actuators every single second. It's the silent conductor of this incredibly complex orchestra. Now, putting all those parts together sounds pretty straightforward. But doing so brings us face to face with the single biggest challenge in all of humanoid robotics: just staying upright.
I mean, walking on 2 legs, it's something we do without a second thought. But for a machine, it is an absolute physics nightmare. See, unlike a table with 4 legs, a 2-legged system is just naturally unstable. It's basically in a constant state of falling and catching itself with every single step. And that requires an unbelievable amount of constant calculation.
And this comparison here really drives the point home. For us, balance is intuitive, subconscious. For a robot, it's just brute force math running nonstop. We can instantly adapt to a slippery floor. A robot is completely at the mercy of its sensors. And all of that thinking and moving, it just burns through a massive amount of power.
And as if that balancing act wasn't tough enough, engineers are also wrestling with 2 other massive hurdles. First up is perception. I mean, it's one thing to walk across a clean, flat lab floor. It's a whole other ballgame to navigate a messy living room and figure out what's a toy versus what's a step you're about to trip over. The second one is power. All those computers and powerful motors are incredibly thirsty for energy. Just finding a battery that can keep the whole show running is a huge challenge all on its own. So, with all these incredible challenges, you've got to wonder, why bother? Well, because the payoff for creating a robot that can actually navigate our world, it's potentially enormous.
And this is where all that hard work could really pay off. We're talking about robots that can step carefully through the rubble of an earthquake to find survivors, or use the same tools as an astronaut to fix something on the outside of a space station, or even just gently help an elderly person get out of a chair. These aren't just far-off concepts. These are the real-world goals that are driving all of this research.
So, if you remember just one thing from this explainer, let it be this. The humanoid shape isn't a gimmick. It is not about making a sci-fi dream come true. It's a practical, strategic design choice to create a machine that can operate seamlessly in a world that was, until now, built exclusively for us. You see, the technical hurdles, they're falling away one by one. The engineering problems are being solved. And that's leaving us with a much bigger, much more complicated question for the future. As these things step out of the lab and into our lives, the focus is going to shift from engineering to society.